Good morning and welcome to the Arm Dev Summit. My name is Ashwin Matta. I'm Director of IP Product Management. My focus is on servers and HPC systems. Today I'll be talking about how Arm is making a big wave in the HPC arena with its own custom design processors. Uh, you must have heard a lot about Arm in the news in the past few years, especially in the HPC space. But today's talk will be focusing specifically about IP that we are designing to target this specific market. So what is this new HPC wave we are talking about here? There are three main trends which are part of this change. The first one is accelerating adoption of HPC in the cloud. And this is being driven by multiple factors. For example, the biggest reason is that the cloud is gaining extreme popularity. The systems are becoming more performant in terms of networking bandwidth, in terms of virtual machine performance. It's fully flexible, there's virtually unlimited capacity. And traditionally, people who have been investing in very expensive custom designed HPC systems are now having the option, without any more investment or without any more maintenance, they can move some of their workloads, from these expensive custom designed systems to the cloud. The other very important trend is that the ARM HPC ecosystem itself is gaining leadership position. And as you can see over here in the middle part, there is a certificate awarded to the Fugaku Raiken supercomputer. This is an ARM-based supercomputer that's the #1 in the top 500 right now. Not only is it #1 in the top 500, it's also #1 in the Green 500 and also #1 in some very important HPC benchmarks. This was a custom designed processor called A64FX designed by Fujitsu and deployed within this Raiken supercomputer. The third interesting paradigm is that now there is a very strong push for do-it-yourself SoCs for HPC. And you could partly blame the geopolitical uncertainty, the climate where we are in today, to instigate this type of movement where countries are feeling more and more uncertain about being able to purchase this type of systems from outside, and they want to become self-sufficient and reliant, particularly on the hardware and more importantly on the software side for important applications like security, defense, and advanced research. So the success of the Raiken project and also a very recent announcement from Cypel, where they have announced licensing of the ARM Zeus newer CPU, is kind of showing that this do-it-yourself SoC for HPC is gaining more popularity. So how do we go about building an HPC class ARM processor? I will first talk about an existing CPU, the Neoverse N1 CPU. This is a very common cloud CPU now. It's available freely on the Amazon AWS site as Graviton 2 M6G instance. When we designed the N1 cloud instance, we actually designed it for a very balanced perf per watt per core. So it had all the execution, issue, decode, fetch units as in a traditional CPU processor. But it was designed keeping in mind that not only do we want to get the best performance, but we also want to make sure that the power does not exceed a limit. In terms of floating point capabilities, this is 2 by 128. It supports the Neon instruction set, which is an ARM v 8.0 instruction set. We recently announced another processor, which is a follow-up of N1, and we're calling it the V1, and the internal name was Zeus. This is delivering the fastest performance with a much larger vector pipeline. So in this case, you can see that we have larger fetch decode issue, larger floating point vector pipeline. So now this supports a 2 by 256 bits SVE, which is scalable vector extension, and a larger bandwidth to memory to process all the transactions. So technically, both of these CPUs are excellent, both for the cloud and for HPC. But the V1 would particularly shine in the HPC market because of its SIMD capabilities. By having a larger vector pipeline, it can process and more memory bandwidth. It can process the SIMD instructions, which are so typical of HPC workloads, in a much more efficient way compared to the N1. So let's take a deeper look at scalable vector extensions. So this is introduced in the ARM v8.4 architecture. And the basis for the scalable vector extensions is to basically enable extending code that is written for one vector size to transition easily to another vector size, and to basically remove several barriers in auto vectorization. So if the auto vectorization works efficiently, then the number of instructions reduces significantly, and that makes the code run at a much higher performance. So some of the techniques deployed by SVE architecture include the gather, load, and scatter store. This is an example where, let's say you have a register which needs to access 4 or 5 different locations which are disjoint in the memory. Then you can do a gather load from these different locations and collect all the results into the single register. The same operation can be reversed for the scatter store behavior. The other 3 examples showcase, how a predication register can control the execution of your SV instruction. So the per lane predication, for example, shows that depending on the value of the predicate register bit, you can either add the top 2 rows, or you can directly copy the top row to the bottom. The next example is showing that how you can determine if you really want to execute your entire vector width, or you want to stop at an earlier index. So you want to do sort of partial vector processing. And that's possible again with the predicate driven loop control and management. Another example at the bottom shows how vector partitioning can be done, again using predicates. And this is very good also for managing complex nested loops where you could have a data dependent exit happening. You can manage to vectorize a complex nested loop in that manner, which was not possible prior to SVE. And the last example is where you can do extended floating point horizontal operations. So you can take parts of a vector and either add them or subtract them, multiply them together. So with a combination of these techniques and a lot more, SVE is making a big impact on the performance of the vector operations which are executing. So let's take a look at how SVE compares with the x86 equivalent, which is AVX 512. AVX 512 has been around for some time and has some developer challenges. For example, if AVX 512 is enabled on the entire 512-bit data path, then typically frequency from the standard sort of turbo mode, which is in non-AVX operation, would fall by as much as about 25%. So the advantage of the vectorization is partially lost because of this lower frequency. The other issues have been pointed out in some online blogs, one of them by none other than Linus Torvalds himself. And this refers to the occasional use and the fragmented support problem. What happens is that if you have code that is a combination of SSE and AVX 512, SSE being the previous version of AVX 512 at a lower width, then as you're transitioning vector execution from 512 to SSE, you could potentially dirty the FPU state. And the only way you can recover is by saving the entire state, sort of doing like a reset and then recovering. This actually makes it pretty impractical to use in realistic cases. Also, the portions of the x86 install base that currently don't support 512 cause challenges for developers to manage the execution on this AVX 512. The advantage SVE has is that it's come later and it has learned from some of the challenges from AVX 512. The first one is, of course, that being built on top of ARM, silicon partners have the advantage that they can control their voltage and frequency transitions, And because ARM is inherently a low-powered core, there's a lot more headroom before which you have to adopt, power-saving techniques like frequency throttling. The other more important advantage is that SVE is natively architected to scale between very narrow 128 bits and can go up to 512 and even all the way up to 2048 bits. This can be done at runtime. So let's say you've compiled your code to run at a certain width, on a certain system, let's say 256-bit system, and then you want to target a 128-bit system, you can do that dynamically without having to touch your code again. So starting with Nuverse V1, all the ARM Nuverse CPUs will support SVE, and we are making sure that we continue the support going forward with enhancements for SVE for more performance improvements. So let's compare the N1 and V1 based on the native number of vector operations per CPU clock. So obviously, as you know, that V1, as I mentioned, that V1 is 2 by 256, so it's got a 512-bit vector pipeline, whereas N1 is 2 by 128 or a 256-bit vector pipeline. So if you look at FP64 execution, the V1 can theoretically execute 8 operations in a single clock cycle versus 4 for N1. The next data type is BF16 or bfloat 16. This is relatively new data type that's used extensively for machine learning. For BF16, there is no support on N1. There is only support in the microarchitecture for V1. V1 can execute 64 BF16 operations theoretically, in the single clock cycle. And the more common integer 8 operations are as many as 128 can be executed compared to only 32 on the N1. Now, the reason you get that additional 2x multiplier for BF16 and int8 is because the V1 processor implements this MMLA matrix multiply operation. And as a result, you get an additional double performance speed up in terms of the total number of operations that you can perform in a single CPU clock cycle. So pretty impressive overall, going from just being able to run in a scalar mode to being able to run up to 128 int8 operations in parallel. Now, all this would not be possible if we were not enabling our ecosystem with software. So there are 3 main categories of software enablement for Arm HPC processors. The first major category is code generation. So this includes things like C, C++, Fortran compilers, which have been now very well optimized for scientific computing and HPC workloads. There's also support for the ARM V8A and SVE architecture extensions. Performance optimized 64-bit math libraries are also very important, for this type of market. The other set of tools which are being provided are to basically improve the performance. Basically, you can do things like debug and trace, thousands of processor nodes. You can do profiling of your code, not just of the CPU, but also of GPU and I/O. And that way you can look at where the HPC algorithm bottlenecks are. There's a lot of smarts which have been built into the error detection, which is very important when it comes to debugging issues with the memory. And all of this is combined with extremely good analysis reports with metrics, etc. So now you not only have the generation, but you also have all the visibility into how your code is performing. And last but not least, ARM is very active in the open source ecosystem for HPC. So we are very actively working on the roadmap improvements for GCC, LLVM, and CLang compilers, including the support for SVE and the next generation SVE2. And we are also making sure that the virtual platforms of our processors are available to our partners even before the silicon is available. That way, they can get access to the architecture as well as an execution model of the CPU and start developing the software or porting the software from older CPUs to the newer ones, way before silicon is ready. So now let's take a look at some of the workload performance of ARM-based processors. Now, we are comparing, in this case, 4 different systems. Now, this is the only data that I'm showing that has been benchmarked on real systems. The remaining data will be based on simulations. In this case, the 4 systems are a Marvell TX2 Stria, which has been installed at Sandia National Labs. This is a Marvell design custom ARM v8.1 CPU core, and it's basically a miniature version of, I mean, the TX2 Stria is a miniature version of the Astra supercomputer. The other 3 are all from Amazon AWS. So for example, the M6G is the ARM v8.2 Neoverse N1. So this is using the ARM IP. And the other 2 are the top of the line IPs at that time from Intel, which is Cascade Lake, and from AMD, which is Naples. Now, all the AWS systems have 64 virtual CPUs. So to kind of do an apples to apples comparison. And with TX2, we were not able to find the exact configuration. But then, given that the TX2 system is older generation compared to the AWS systems, we thought it was acceptable to, run 112 threads, and they're running at a lower frequency compared to the AWS systems. The caches and memory sizes were optimized, the best possible or the maximum possible that was available on these platforms. The workload we were actually running is a well-known workload called Nalu, developed by Sandia National Labs. It solves a low Mach number Navier-Stokes equation using an unstructured 3D mesh. So in this case, for example, we use a mesh which has about 2 million elements. The good part about this workload is that it exercises, multiple software packages which are commonly deployed, by different HPC applications. And it's scalable to a very large number of cores. So more than 500,000 cores, you can operate with this workload. And the specific test experiment that we were working on in this measurement was to kind of emulate an open jet, a mixed fraction based turbulent open jet with a Reynolds factor of about 6,000. So here are the results. On the left side, you can see relative simulation time for the benchmark to complete, and obviously lower the time, the better. And everything here is relative comparisons. So if you look at AWS ARM implementation on the M6G, that has the lowest time and hence the highest performance. The next in line are almost 20% higher, which is both the TX2 as well as the AWS Intel. Now, another interesting metric is to see that if I have a certain workload that I want to run in HPC, how much is it going to cost me, right? And the cost is determined by 2 factors. It's determined by A, what is the cost of the platform, on which I'm running it, on an hourly basis. And secondly, second is, what is the performance, obviously, which we measure on the left-hand side. So if you do this comparison of cost, which includes both these factors, the AWS ARM instance is almost 70% better in cost to execute that workload compared to the x86 instances. We've also done analysis of other HPC workloads, which are, and showing that, we're getting similar dollar advantages, which is around 70%. Now, the next benchmark I would like to show you is the HACCkernels Benchmark. And this was run using the ARM compiler 20.1 version. Now, in this case, we are comparing only the ARM CPUs. So we're comparing the older generation Neoverse N1, which is v8.2, and the newer generation V1, which is v8.4. And we're comparing only single thread performance on cycle approximate simulation models. So we're doing single thread comparisons because, because this is simulation, it's not possible to have, a large 64 or higher core count running effectively on a simulator. The HACCkernels benchmark setup essentially comprised of, the source code, of course, which was a computationally intensive part of an n-body cosmology code. The source code is very little, but there is an inner loop that gets vectorized actually extremely well. And I'll talk a little bit about the results we get. And then the way we benchmarked this was we first ran it on N1 and V1 using the Neon instruction set. That means we did not enable SVE. And then after that, we enabled SVE only on V1, since SVE is not supported on the older N1 on the N1 processor. So if you look at the results here, we are seeing a very improvement of about 46% from the N1 to the V1, just operating in the neon space. So 46% here is kind of I would call it the native performance improvement, right? Going from N1 to V1, which means because of the better microarchitecture, bigger caches, etc., you are getting, and of course the larger neon vector pipeline, which is the most important reason. You're getting an overall 46% improvement. But then when you enable the SVE, you get an additional 25% performance. So it goes to an 82% improvement compared to the N1. In terms of instruction counts, in the first two experiments, the instruction count remains the same because it's still using the neon instruction set. So there's no drop in the number of instructions. When you switch to SVE, you get a 38% drop in the number of instructions. So it's just showing how good a job SVE is doing on the vectorization. And obviously that is the reason why you're seeing a lot of speed up as well. Now, the interesting observation we made, when we analyze this data even further is that if you compare the vector execution on 512 bits versus a pure 64-bit scalar execution, the execution is the vector size is 8 times, right? The scalar size, and the performance we were able to see on the inner loop, which is very well vectorized, is 7 times improvement, compared to or just on the inner loop. So that just shows that the SVE is almost 87.5% or 90% efficient for converting this inner loop into instructions that are running on the SVE vector pipeline. So let's take a look at the next benchmark, the HPCG. The HPCG benchmark implements sparse matrix multiplication. It's a benchmark that heavily stresses memory access patterns. Now, in this case, we compiled it using GCC 10.2, which has SVE optimizations on it. We ran it on N1 and V1, and on V1, we actually had 2 levels of SVE optimizations. The first was just generic SVE optimizations. So we were applying general parallelization techniques. And this is a very common acceptable practice, when you're trying to optimize your performance. On the second level, we went in there and took a look at some very low level compute intensive routines and hand optimized them to replace the floating point code with SVE code. Now, the reason we had to do that is because SVE is still fairly new technology and the compilers are just beginning to support them. So there is headroom to grow in terms of compiler performance. And we expect that, in future versions, the compilers will be able to do this automatically and you won't need that hand optimization. So if you compare the results, the first level of V1 is about 71% better in performance compared to N1. And then with the hand optimization, it goes up to 83% better. This result is actually pretty similar to the previous one where we had seen that the V1 SVE is about 82% better than the N1. The instruction count also is good. Like it goes from 41% improvement, when you go to the first level optimization to a 48% improvement when you go to the second level optimization. So to summarize, there's very strong growth going on in the ARM-based HPC systems, both from a IP perspective as well as custom architecture implementations. This is driven by various factors like HPC growing in the cloud, countries wanting to develop their own systems for self-reliance, and overall ARM hardware software ecosystem growth. ARM's next generation CPU, the V1 processor, is designed with features for hyperscale and HPC. It's extremely high single thread performance. It's got really good caches and memory bandwidth, and it has a larger 512-bit vector data path with SVE support. ARM is deploying ARM-based processors deployed in the cloud today, which is mostly on the Amazon, are exhibiting superior performance on important HPC workloads compared to the corresponding x86 high-end solutions. And overall, we are seeing that the Neoverse V1 on our simulations is showing an 80% improvement in performance on key benchmarks over existing N1 solutions. Now, again, this is single thread performance, but when our customers will build their eventual systems, then we will be able to look at the overall improvement in the socket level performance. I can strongly say that this is just the beginning for ARM IP in HPC. There's plenty of headroom to grow both on the processor side and on the SVE compiler side. So we are looking forward to more exciting news on these topics in the next few years. Thank you for your time, and I'll be happy to take any more questions.